the nanoparticles. The entire synthesis for cadmium selenide is quite rapid. In this setup, it takes about 5 minutes to go to completion or can be stopped earlier to obtain smaller sized nanoparticles. As the reaction progresses, we can see that the color of the solution changes. This is because quantum dots have optical and electronic properties that are dependent on their size. Here we're taking aliquots at different time points in the synthesis so that we can have cadmium selenide quantum dots of different sizes to compare to one another. When we compare the different aliquots, we see that they exhibit colors ranging from yellow to reddish orange. This is because of an important feature of quantum dots where their absorption maxima vary with the size due to the quantum confinement effect. As a reaction progresses and the particle size increases, the absorption feature progresses to higher wavelengths. These absorbance features can be measured by UV-Vis spectroscopy. This peak seen here shows the lowest energy excitonic transition and corresponds to the band gap energy of the semiconductor. Fast cell characterization of the optical properties is a major advantage because as the reaction progresses, the size of the quantum dots can be estimated by the wavelength of this peak. More accurate size measurements can be done via transmission electron microscopy. These particles are also naturally luminescent, and so their emissive features also vary as a function of size, as you can see here. The smallest particles emit in the blue and the largest in the red. While the synthesis of cadmium selenide quantum dots is very well developed, cadmium-based materials are avoided in applications for their high toxicity, so there's a big push towards developing less toxic alternatives. Indium phosphide is a less toxic alternative that is being used as a drop-in replacement for cadmium selenide nanomaterials currently in commercial display applications.